So we're jumping all the way to the end of our textbook to cover in 2 lectures a unit on nuclear chemistry and nuclear reactions. So split basically into 2 different sections. The first is going to be on writing and balancing nuclear equations, and then the second is going to set us up to think about what is going to be the 4th learning unit, which is kinetics, which is how fast reactions occur. And so this second skill we're going to have is on first order reactions, for which nuclear decay is one of them. So we start out here with just how we write nuclear reactions. So just as kind of a broad strokes overview, we've been focused mainly on thinking about chemistry as it happens with electrons, whether it's sharing those electrons for covalent compounds or trading electrons with ionic compounds. And what's different with nuclear chemistry is we're concerned with the properties of and changes to the atomic nuclei. So protons, neutrons, and so forth. So again, traditional chemistry, as we've been thinking about it, involves properties and changes related to the electronic structure of atoms and molecules. So it's a shift in gears, but an important part of the field of chemistry. So some terminology, a little bit of it is review, some ways that we need to think about sort of a formalism for how we write things. But remembering that there are 3 subatomic particles, electrons being the first, there's also protons and neutrons that are in the nucleus. So here's how we abbreviate protons, a P with a plus symbol reminding us that it's positively charged, and it has a mass of 1 atomic mass unit, and then this little 1 here helps us remember that it has a charge of 1. Neutrons here, as the name implies, have no charge, they're neutral, and they also have a mass of 1. So when we think about kind of a formalism here for how we write things, this was something we introduced last semester, but we have an atomic symbol, and then on the left upper and left lower side of that, we have the atomic number, which is also the number of protons. Remember, that's how we chemically identify a substance, by the number of protons it has. And then the mass number is a larger number that is usually written in the upper left, and that's the sum of protons plus neutrons. So you can't change the number of protons that a substance has without changing its chemical identity. It'll be a different element. But if we change the number of neutrons that it has, we can create what are called isotopes of a certain element or of a certain compound. So isotopes are going to have the same number of protons. So by chemical identity, they're the same substance, but by having different number of neutrons, they'll have different mass numbers. So here we can see here is an isotope of carbon that has 6 neutrons and 6 protons. Again, by having 6 protons, that makes it carbon. It is the carbon-12 isotope by having 6 neutrons. One of the important isotopes that we'll talk about with carbon is carbon-14. Carbon-14 is going to have 8 neutrons. That's important because it's a radioactive isotope that can decay, and we're going to learn how you can use it for carbon dating. Just another example here, again, you can have 2 more neutrons as well as 2 more protons to give you an isotope of oxygen. So this is, again, a naturally occurring isotope of oxygen. All right, this is a really important slide. I'm going to kind of highlight, this is information you must know. This is, again, as you're working through this content, have this sheet available to kind of help you, but this is something that's going to require you to kind of have it up here so that we can think about writing nuclear equations using these different pieces. Okay, there's 5 different particles that we want to think about in terms of being involved in writing nuclear equations. The largest particle is what we call an alpha particle. It's really a helium nucleus. A helium nucleus has 2 protons. If we think about helium and where it is in the periodic table, it's atomic number 2, so it has 2 protons. An atomic mass of 4, meaning there's also 2 neutrons. And because there's no electrons, it has a charge of +2. So it's just a helium nucleus. Sometimes you'll see it just abbreviated with alpha. But again, the mass is 4 from 2 neutrons and 2 protons. And then the charge is +2. Okay, so because this has both mass and charge, when this atomic particle, or when this particle is used in nuclear processes, it's going to result in changes in atomic mass, changes in atomic number, we're going to change the element that we have, and then changes in charge. So this kind of balancing of chemical equations is going to be unique because we're not balancing the same number of atoms on the left and right side, because we're actually doing chemistry that changes the identity of an atom. There are 3 different kinds of ways we see electrons in nuclear equations. We see what are called beta particles that are emitted. Okay, this is a high-speed electron that's emitted from a radioactive species. It's abbreviated like this. Okay, we can see here this reminds us that it has a -1 charge. It has no mass. And you can sometimes see even written with an E for an electron or a beta, that beta to indicate it's a beta particle. But because this is going to change charge, and again, we're going to see that down here, this is going to be an important piece to have us see that it changes the atomic number as well. So this is, again, the formalism. You want to know that that's how you write a beta particle, okay? Positrons are sort of like the opposite of electrons, and what's different here is it's +1 charge, and we can see that that means there's a +1 down there. I'm not going to go into the details of why we have these numbers down here, but you do need to remember those so you know how to use these species when you're writing a nuclear equation. And then the second piece, or the third piece, the third way that we kind of see electrons is seeing electrons through what we call electron capture. So electron capture means these are going to be electrons that appear as reactants. As we talk about how you write nuclear equations, one of the things we'll discuss here is making sure that you put certain species on the correct side of an equation, whether it's a reactant or a product. This is a common place that students can make mistakes. So again, 3 different ways that we see electrons. The last thing actually does nothing to change atomic number, charge, or mass. This is just energy that's emitted, and we call this a gamma particle or gamma emission. These zeros here remind us that it's not going to do anything to change charge or atomic number. Okay, but it is something that maybe you'll see that you're adding gamma irradiation to an isotope, or maybe an isotope is emitting gamma radiation. So these are the important pieces. I'd encourage you, as you're working through and learning how to do these problems, have this table nearby. But when it comes time kind of for a test and so forth, these are pieces of information you have to have in your brain. All right, so what is a nuclear equation and how do we write them? Well, a nuclear equation is not unlike other kinds of chemical equations that we've seen, but we've got new pieces to think about since we're talking about the gain and loss of subatomic particles rather than, say, the gain or loss of electrons. So a key to writing and balancing these is to understand that the mass and charge of all reactant species must equal the mass and charge of all reactant species. So this is kind of a generic equation. So maybe when we were talking about balancing chemical equations, we had to balance the number of atoms that were on the left and the right side. Okay, now what we're going to see here is everything that adds up on the mass part and everything that adds up down here on sort of the atomic number part has to be the same on the left and the right sides. So once we do an example problem, hopefully this will make sense. All right, so how do you write a nuclear equation? 3-step process to help us do this. The first step is to write a skeleton equation that comes from information that's provided, making sure to include things like mass numbers, atomic numbers, symbols for all the particles that they've provided for you and given you information on. And importantly, we need to make sure that we put them on the correct sides. Everything's going to kind of be in this format that we talked about on a previous slide. Common mistakes that students can make is they don't put things on the correct side. So there's some terminology we want to make sure that we understand that gives us information about which side something is on. If something is emitted or referred to as decay, like alpha decay or beta decay, that tells us that these particles are products. We're going to write them on the right side of our chemical equation. If you see words like bombarded with or reacted with, that tells us that those are species that belong on the left side, on the reactant side of an equation. If a problem talks about electron capture, just like we saw over here, we're going to write an electron just like we saw for a beta particle, but electron capture is always as a reactant, always on the left side. So things that you might need to have at the ready as well are a periodic table, because you might need to look up an element based on its atomic number. You might need to take a name and find out how many protons that has. And again, atomic mass, just remembering that atomic mass is the number of protons plus neutrons. So maybe we might need to use that atomic mass number to figure out how many protons something has if we know something about the number of neutrons. So second step after we've written that kind of skeleton equation is something is going to be unknown. Maybe the isotope that we started with and decayed into this product, or maybe we want to know what an isotope decayed into. So the third step then is trying to figure out kind of what that unknown is, and remembering that the mass numbers and total of charges on the left and the right side need to be equal. We can figure out what that unknown is. So again, I'm going to show you an example on the next slide, but basically everything that's on this upper part of our of all of our species on the left need to add up to what's on the upper part on everything that's on the right. Okay. We have to make sure we take note if we're adding a negative, which really means we're subtracting. So again, that's something to think about. And again, have a periodic table at the ready because you might generate a new element that you then need to use a periodic table to figure out who it is. All right, one quick example, and then we'll have lots that we'll go over in class here. So just because here's two things you're going to want to have at the ready as you do these problems, you want to have this table, right? At some point, you're going to need to know this information, but have it ready while you're practicing, and then obviously a periodic table to look up things. So this problem tells us we want to write a nuclear equation for the naturally occurring isotope thorium-232 that undergoes alpha decay. All right, so we know two pieces of information. They tell us we start out with thorium-232. So again, if we don't know where that is, let's look up in the periodic table. One of the things that we're going to see a lot of in this unit is we're going to see a lot of stuff from the lanthanide series, some of these heavier metals that are radioactive. Okay, so here's thorium. You can see that the naturally occurring isotope, it is not surprising that it has the same as what we see on the periodic table. We talked about that last semester. But again, the atomic number is 90. This is why we needed the periodic table, because we needed to be able to write this guy as its full kind of name. So it's 232 goes on top. That's the atomic mass. Thorium is the chemical symbol, so we're going to write it there. And then importantly, we needed the periodic table because we needed to figure out that it had the atomic number of 90. So that's where we got that piece of information. All right, so we're talking about the decay of this, which means it's going to be converted into a different element. So we're going to convert it into something else. And how do we figure out what something else is? Well, we know that it undergoes alpha decay. Okay, so alpha decay means we're going to make this guy on the right side. Okay, so that means we're going to have an alpha particle. So 4, 2, and then helium. And for right now, don't worry too much about the charges, okay? So we know that we generate an alpha particle. So let's kind of highlight where we get our pieces of information here. So this guy, we had to look up on our periodic table. It's right there. And then we know we generate an alpha particle, okay? So again, tells us that we undergo alpha decay. That the decay piece tells us that it appears on the right side. Okay, so now the last piece is we need to figure out what else is left over, okay? So some element is left over. Here's how we figure out the pieces that are left over. We've got essentially two boxes we need to fill in here. So let me call this box number 1 and then box number 2. So what we really do is a little bit of algebra here. We're going to say something plus 4 must equal 232. Well, that tells me that this must be 228. Okay, same thing down below here. We've got something plus 2 equals 90. Well, that must mean that this is 88. So now what I need to do is take these pieces of information, go back to my periodic table and figure out who this is. So if I look up things here, I can see, well, let's see, this was 90, right? This was 90 here. This is 89. Here's 88. Ah, it's radium. Okay, so that's going to be radium. Okay, radium has 88 protons. Nothing else can have 88 protons and be anything other than radium, but I can have different isotopes of radium. So this is going to be what we call radium-228. So I could provide it in this format, or I could also write it as this, radium-228. And again, I know that it's going to have 88 protons because by definition, that's the chemical identity of radium. Okay, hope that helps you get some starting practice for how to write nuclear equations.